Hello everyone. I'm Azman and I'm working with Dr. Banerjee and Dr. Pittman on understanding the understanding the behavior of Syria on dope conditions. Um, so Syria is one of the rare oxide that is has good optical properties such as the ion transparency, and also it has been used in optical applications as well. Doping can affect those optical properties such as the electronic structure, and the catalytic activity can be affected by doping. And rare oxides have been used in experimental studies to enhance properties of cerium oxide to obtain those properties. What we are interested in the behavior of cerium oxide under dope conditions, mechanical behavior of or mechanical properties change of cerium oxide under dope conditions. Last year this time, I presented on the validations of my work. So what we do is we perform molecular dynamics to produce equilibrated structure of cerium and yttrium oxide to validate the force field, as well through the structures, as well as the mechanical properties using the bulk modulus as our benchmark and the structure factor and RDFs. What we see is that what we saw that there is good agreement with the experiments and previous experimental previous computational work for dope cerium oxide with the particular force molecular dynamics force field we had used. Our goal of the study was to understand the effect on the effect of dopants on the mechanical properties of Syria. So we conducted some static calculations using those force field that we had been validated. What we see is that as we dope cerium oxide with gadolinium, europia, and yttria, we see a linear decrease of mechanical properties such as the C11, the elastic properties such as C11 and the bulk multiplier. But we also studied zirconium oxide, doping zirconium oxide into cerium supercells. What we saw is that there is an increase in mechanical properties such as the C11 and the bulk multiplier. This was because when we introduced the gadolinium, europia, and yttria, we also introduced to keep this stoichiometry oxygen vacancies, and the cerium and the metals and oxygen interactions were less strong for gadolinium oxygen, europium oxygen, and yttrium oxygen compared to cerium oxygen. That reduce the elastic properties such as C11 and bulk moduli. But in case of zirconia, where we doped zirconia, we did not have to introduce oxygen vacancy there, so there was no oxygen vacancy or point defects. And also zirconia having a +4 charge contributed to the electrostatic interactions as well. Hence, we saw a decrease in mechanical properties for gadolinium, europia, and yttria, but improvement of mechanical properties in case of zirconium oxide doping. To understand that, we studied the cohesive energy of the doped system. What we saw that there is a decrease in the cohesive energy overall for the gadolinium, europia, and yttria, but an increase in case of zirconia. This decrease is due to the weaker metal and oxygen bonds compared to cerium oxide. We do see yttrium oxide has a slightly higher cohesion because of a deeper depth of well per se in our potential energy versus the distance curve. And for gadolinium, however, what larger dopant did is they had higher lattice distortion, so further decrease the cohesion in the lattice. For zirconia, we see the increased cohesion and cohesive energy because zirconium oxide having higher electrostatic interactions also had a deeper depth of well, so a higher interaction or a higher energetic interaction proved to cause a stiffer lattice that increase the cohesive energy. Dopant size also has an impact, where the large dopant increase the lattice distortion, weakening the cohesion in the lattice, and the smaller dopants maintain the stronger electrostatic interactions. So, in case of Europia, we see a higher drop in the cohesion. To understand that, we dive deeper to look into the local structure of those crystals. We were interested in the distribution of the oxygen vacancies, dopants, and the metal ions itself. What we found out that as we dope with higher concentration of metals, the distribution of potential energy of each atom, the distribution of the potential energy has increased or broadened, and also what we see is that due to the lattice distortion presented in the CSP, or the centrosymmetry parameter, describing the centrosymmetry parameter, there are higher lattice distortion into the system that caused a wider range of potential energy in those dope systems as we kept increasing the dopant concentration. We also conducted the centrosymmetry parameter analysis, where we saw that higher gadolinium content increases the centrosymmetry parameter distribution, which indicated a greater lattice distortion. Also, an oxygen vacancy situated near the oxygen vacancy situated near the dopant ions also had a higher 42% higher potential energy, and as the gadolinium and oxygen had a weaker interaction, that broadening amplified. The elastic properties we calculated using the static model that we used before is highly affected by the change of the per atom energy, because the virial that is being calculated is proportional, or virial that is calculated has a term that directly controls or directly affects the virial that is directly affected by the potential energy term. So far we have found out that yes, doping does affect the mechanical properties, and the oxygen and the metal and the dopant interaction is the biggest contributor to that change. And also, if we introduce more and more oxygen vacancy, that will deteriorate the overall oxygen and overall mechanical properties of the supercrystal. Building onto this, we started our next project, which is we are looking into the mechanical behavior of the same doped and pure cerium supercrystals. So what we initially did is we took a sample of those, or we took those dopant structures and put them in an in silico tensile test to see how they respond to stresses. And what we see is that for pure ceria, a phase change during the tensile regime after some certain strain, after some certain strain limit. This has also been reported in literature previously, but now we want to see how doping can affect that phase change during the tensile loading. It is reported that during tension, cerium oxide goes from fluoride phase to a rutile phase to two different phases as well. We wanted to see if the doping affects that phase change, because those phase change is accompanied by slip of the stacking faults, and also affected by the dopant concentration as well. And also we wanted to know how the oxygen vacancies would play a role in that in the phase change of the pure or doped serious systems. So this is a preliminary results from those calculations, where we see a drop, a 40% a drop of strain to failure, a 40% drop of strain to failure when we dope the pure serious system to 20% gadolinium, and we also see that during the loading, that phase change that occurs from FCC. This is I'm just showing the sublattice of the metals. As we strain, the FCC sublattice of metal changes to BCC sublattice and then to HCP before failing. But in case of gadolinium doped ceria, we do not see that complex phase change. We wanted to further study this in the coming past years. I would like to thank Dr. Banerjee and Dr. Beckman on this for helping me out, and also Dr. Barr for contributing to this project as well. Thank you.
Next time, please go up the plots. It's kind of hard to see.
Oh, yeah.
So at the beginning, you said you also did calculations starting from zirconia and doping zirconia, right?
We dope cerium oxide with zirconia.
Right, but I thought you also said that you did it the other way around too. Is that not correct?
No, we haven't done the other way around. We haven't doped zirconia with cerium.
So how much zirconia did you put in cerium?
The highest concentration was 20 more percent.
20 more percent of metal?
Yes.
I don't think you're gonna see a phase change there yet, but I recently reviewed a very, very good paper. I don't think it's out yet. But they did the full solid solution between zirconium oxide and cerium. And there's about 5 phases. Most of them are towards the zirconium end, but there's, monoclinic, tetragonal, there's 2 different metastable tetragonal phases, as well as the cubic phase. So you're assuming, or you only have the cubic phase in your
Yes.
system?
Yes. Heading on to that, are those phases a certain concentration, or do we have a range of?
Their range, you can't, it's difficult to tell from diffraction for some of these because they're superstructure ordered. But they're not cubic, so they're gonna have more than one elastic frame. That's why I asked the question. But if you're only in the cubic domain, then
We are still, for those static calculations that we did for the mechanical properties, we are still in the cubic domain. And as the way I make the structures, I randomly distribute the zirconia replacing the ceria. So we have not seen any other phase being segregated and forming other different phase, and that has not affected calculations. But yeah, that's a good comment to incorporate in the study as well.